we're given for problem 2 the wave function as psi of x, which means it's independent of time, and the Schrodinger time-independent equation is given in the second line. If this wave function is a valid stationary state wave function, then it must satisfy the time-independent Schrodinger equation, and it has to have a u of x equals 0. So if stationary state solution, it implies that u of x equals 0, and that means that we want to test whether psi of x is psi of x a solution or satisfies the equation minus h bar squared over 2m, second derivative of psi with respect to x. Does that equal e times e of x? And plugging in this equation, we get minus h bar squared over 2m times the derivative with respect to x of a1 e to the I kx plus a2 e to the minus I kx, and that equals minus h bar squared over 2m times, we're going to pick up, if we take the derivative of the first term twice with x, we're going to get an a1 times I k1 squared e to the I k1x plus a2 times minus I k2 squared e to the minus I k2x. And simplifying this a little more, this gives us h bar squared over 2m times k squared, because k1 equals k2, so I didn't need to put those, that's just a k, times a1e to the I kx plus a2e to the minus I kx. And notice that this is the same as h bar squared k squared over 2m times the original psi of x. So it does satisfy the equation, which is a constant times the original function was equal to minus h prime squared over 2m times the second derivative of the wave function. And so we can say that the energy in this case would correspond to h bar squared k squared over 2m.